Hi, this is John Ellis again, and we're going to talk today again about what optical engineers do. And with me is Sergey Sidorovich, who worked on this program for us a few years ago. Welcome, Sergey.
Hi, John.
And in this particular project, we had a customer who we had designed a lens for. The lens was to work with a liquid lens, and their application was looking at different kinds of small codes, barcodes and QR codes. And in my recollection, our customer came to them and said, there are these new QR codes on the market. They're extremely small. Could we use the same optical system to read them? We would maybe change the object distance. Maybe we'd use a different camera, but we're wondering, could we use the same lens stack and combination to read the lens? And so they asked Sergey to help them figure out the answer to that question. And this is a report that Sergey, you prepared. So let's just look at the work that you did. Why don't you take it away, Sergey, and tell me what you remember about this particular program.
Yeah, and this was a good question regarding the current optics for the new task. This saves time, money, and engineering time. Okay, and to understand can we work with smaller code, we need to make several simulations, and our idea was to place the code closer to the optics. In this way we make magnification better for this task, and also we proposed to make distance between the sensor and lens also longer, and try to focus on the close placed object with help of the liquid lens. And so we put everything into the optic software. We format a model for this and started exploring of this question to understand what we can do with this. In addition to these actions, we decided to try different pixel sizes, different camera sensors. Smaller pixel size allows to achieve high pixel resolution, but for this task, as I remember, the main issue was not in the pixel resolution. The main issue was in the optical resolution, because very close placed objects not always can be good focused at the camera.
And this is the layout, and I guess in your ZMAX simulation you would have included all of the windows, the liquid lens, the custom lens, even the sensor protect glass, which because this presumably is going to have some impact on optical resolution, so you needed to account for that in your simulations. Is that right?
Yes, is it right? Because we worked in the lens worked in conditions very close to the physically possible limits. This is why we need to take into account everything that can affect the quality of the image.
All right, so let's look at the work that you did. Grayed out some of the information. I just don't think it was necessary, but you can see that you were looking at many different distances. You looked at, I don't know, what is it here, 12, 15 different distances, each with a different field of view. And as the field of view changed, the magnification changed. Maybe you could talk more about these what we can learn from this slide.
Well, in this, the two main columns is the two last columns: resolution in the image plane and requirements for the resolution in the image plane. As I remember, we defined requirements for the resolution in the image plane to provide possibility to read these codes. Software requires optical resolution to read these codes, and we did series of simulations and defined resolution in image plane in the model, and compare this achieved resolution with the resolution that is required for the software. And now we can see results of this work.
And you have this here, line pairs per millimeters at 0.2. Am I correct that that's a contrast value? Is that right?
This is a contrast, yeah.
At a 0.2 contrast is kind of the limit of what a image sensor could resolve, right? I mean, if you get less than that contrast, it's going to be a poor image. Is that?
No, not the image sensor. Software, as a rule, this is software limit. Generally, almost each computer vision application requires minimum 0.2 contrast for good functioning. But now I know that these limits become slower, and images with lower contrast also can be readable with help of new features in programming and image processing.
Okay. All right, so there's the optical resolution. And now, how is that different from this next slide here? We still have the same distances, same field of views and magnifications, but you're expressing this information differently.
Yeah, in optical system, when we work with camera, we have two resolutions. This is an optical resolution, and this is a possibility of the optical system of the lens to form image with some contrast for some defined optical resolution. And this resolution we indicate and estimate in line pairs per millimeter. From another side, we have a camera that divides our plane image formed with help of optics with help of pixels. And even if we will have beautiful and very high contrast image formed by the lens, and in the same time we will have a very low resolution of the sensor, the image will look not good, and I hope that everybody understands what I mean. From another side, sometimes we see another situation when the sensor has very high resolution, and the optics cannot provide so high optical resolution to not to correspond this sensor high resolution. And this is smaller problem than previous, because okay, we have not very sharp line, but it is imaged by huge numbers of pixels, and image it will look better than the image with lower pixel resolution. In this case, we have requirements for number of pixels per one element, and from another side we have smallest element image. It means that at the sensor we have small projected image of the code, and this size of the smallest element is 7.8 micrometers, and software requires 2.1 pixel per this element. And if we see that pixel size is 3.75, it looks like it corresponds.
Okay, so let's look at the actual images here, and you're changing the object image, you're putting a code into Zmax and looking at the number of pixels at different object distances, and you're using the pixel size from a camera that you found, the Optical camera. So what did we learn from this slide?
Okay, here we use different magnification, different placement of the code to understand relations between the optical and pixel resolution. And on the right image we can see that QR code look pretty sharp. It can even probably be read it, but on the right, in the center image and on the right image, we can see that images have low pixel resolution. You can see that different dots, they cannot be resolved by the sensor, and this is why these codes will not be readable.
Okay, so now we have to figure out, well, if it's not going to be readable at those object distances that they had hoped, what are the next steps, and what were your conclusions here?
The main conclusion is that we need to increase pixel resolution, and this can be done with help of smaller pixel size. So we need to find a camera or the sensor with a very small pixel, and these three images provide simulations with small pixels. On the right image we can see image formed with help of 1.25 micrometer pixel size sensor, and in the center the size of the pixel is 1.67 micrometers, and on the right side the size of pixel is 2.2 micrometers, and the image was done for the same resolution. So these three images were received with the same number of the pixels. This is why we see different size of these images, because of pixel size. And it looks like the first image is the most suitable for our client's application, and it read it well. We even made simulations, not simulations, we tried to read this image with help of clients software, and everything was good.
Okay. And then the other option, I guess, is if they wanted to keep their same camera or keep a camera with a bigger pixel size, they would need to decrease the field of view. But that might have other application impacts of, like, maybe the object or the code wouldn't appear in the field of view. But that was another possible solution.
But the changing of the field of view can require or requires a changing of the optics. So the client, in this way, client needs to replace the lens. The new lens will need longer focal lengths, or also it is possible to propose some kind of adapter front lens that can decrease field of view, but it also contains risk of the lower optical resolution because we change optical design, and so this is a challenge for the optical engineers.
Okay, well, thank you, Sergey. I think this was helpful to our customer and hopefully helpful to people who are interested in this work that optical engineers do. Thanks for talking us through this project from a few years ago. Appreciate your time and look forward to doing this again in the future.
Thank you, John.
Okay, thanks, Sergey. See you later. Bye-bye.
Bye.